All right, so let's get started with the second part of Unit 2. So we're going to be talking about molecules now. So we talked a lot about atoms, right? We talked about isotopes, things like that. But now we're going to start putting the atoms together to make molecules. So we talked about this last time, but atoms are basically like individual units for matter. Now, when we put atoms together, we get molecules. And so easiest way, again, to think about this is like Legos. Atoms are the Lego pieces, right? There's short ones, long ones, red ones, green ones, blue ones, yellow ones, whatever. All different types of Legos, but you put them together and you make the molecule. Same thing with the atoms. Okay, so we got some examples of molecules right here. So one example would be like this one right here. Hydrogen is H2. It is composed of two separate hydrogen atoms, okay? So I'm going to give you guys about maybe 2 minutes. I want you guys to use based on what you know already, and you could work with the people next to you. I want you guys to figure out how many of each element are inside of these two compounds, so 2.8 and 2.9. So I haven't gone over it yet in class, but try to work on it with the people next to you. If this is kind of hard to see, please pull it up on your Chromebooks. It's on Canvas. That way you could see it a little bit better. All right, so I'll give you guys about 2 minutes to work on that. Alrighty, guys, let's go over these. So this should have been pretty simple. Just keep in mind that the subscript, the small number behind the element, tells you how many you have. So there's a 3 behind the K. So you got 3 potassiums. There's no number behind the P, which means there's just 1. So 1 phosphorus. And then for oxygen, there's 4 behind it. So there's 4 oxygens. Okay. Should be pretty simple. All right, 2.9, you had to use these parentheses. The parentheses just mean you multiply everything on the inside by the number on the outside. So there's 1 nitrogen in the parentheses. So you just multiply that by 2. So you got 2 nitrogens. 4 hydrogens in the parentheses, multiply that by 2, you get 8. Okay, so if there's a number on the outside, it just means that there's 2 of everything inside. If there's a 3 on the outside, there's 3 of them, and you kind of just get the point. Okay, so you got 1 sulfur on the outside, 4 oxygens on the outside. Okay, so hopefully not too bad. Just letting you know, I will never, and the AP test will never ask you to do this. I wish it was that simple. This is just kind of prerequisite knowledge you got to know in order to do the more complex calculations later. Only things were that easy, right? Okay, so the formulas that you see here, and this is mostly what you'll see, they're called molecular formulas. And molecular formulas, as you can probably tell, it tells you the actual number of elements in the molecule. It tells you exactly how many of each you have, okay? But there's another type of formula that we work with, and you'll use this on the AP Chem test sometimes. It's called an empirical formula, okay? And so I want you guys to note the difference right here. Molecular formulas are talking about the actual number of molecules. Okay. On the other hand, empirical formulas, they give you the relative number. So in other words, they give you the ratio of atoms inside a molecule. Okay. And so empirical formulas are used most in like experiments. And when we do a couple labs in the future, we will have to use empirical formulas. They're used to try to figure out what the ratio of elements you have when you don't know what compound you're working with exactly. Okay, so that's when it's used. It's more experimental. And then after you guys write this down, I'll go over how to go from molecular to empirical. God bless you. Okay, so going from molecular to empirical is pretty simple. We have an example right here, H2O2. This is hydrogen peroxide or rubbing alcohol. The molecular formula is H2O2. So there are 2 hydrogens and 2 oxygens. Okay, however, the empirical formula is only talking about the ratio between the hydrogens and oxygens. So what we do is we divide by 2 because that's the greatest common factor. And then we get HO. Okay, so 1 hydrogen for every oxygen. And you can see it here. It's 2 for 2. And so it's still a 1-to-1 ratio. Okay, we can do that with glucose as well, C6H12O6. We can divide by the greatest common factor, which is 6, and get CH2O. Okay, so again, it tells you the ratio between all the elements inside that molecule. So if you want to go from molecular to empirical, all you're going to do is you're going to divide by the greatest common factor. You guys might have heard that term before in your math classes. And if you weren't aware already, chemistry is basically all math, so you can consider this another math class. Okay. Any questions on going between molecular and empirical? Hopefully it's not too bad. Yeah. Yeah, exactly. That's another way to think about it. Simplifying the formula. Good point. Okay, so that's empirical and molecular formulas. We'll come back to this later in detail in future units, but now we're going to move on to ions, and this is kind of the basis for the big part of Unit 2. So we talked about isotopes last time, and isotopes are when you have a different number of protons, or yeah, when you have a different number of neutrons in the same element, right? Did you have a question? Sorry. No. Oh, my fault. Okay. Ions are when you have an unequal number of protons and electrons. Okay, so the number of protons does not equal the number of electrons. That's what an ion is. Okay, the opposite of an ion would be a neutral atom, and a neutral atom is an atom that has no charge, and that's when the number of protons equals the number of electrons. Okay, whereas an ion, you have a different number of protons and electrons. All right, now we know that protons are positively charged and electrons are negatively charged, right? And so depending on which one we have more of, we can swing either way in the electrical energy. You can make the atom more positive, or you can make the atom more negative. Okay, so we got an example right here. So we have a sodium atom, and so neutral sodium has 11 protons and 11 electrons. And so when sodium loses an electron, it now has only 10 electrons. So you're going to see that there are more protons than electrons, right? So remember, protons are positive. If you lose an electron, you become less negative. An easy way to think about this is by thinking about this class. This class is probably a negative influence in your life, right? Okay, so if you drop this class, you become a more positive person, right? Or think about a person like me. I'm a negative influence in your life, right? You get rid of Mr. O, you become more positive. Same thing here. Sodium dropped AP chemistry and it became a positive ion. And a positive ion is called a cation. So sodium, it loses an electron, it becomes less negative, it becomes a cation. Okay. And then you can kind of see the other way too. This is probably how you were before you took AP Chem. You were neutral. You're 17 protons, 17 electrons. You gained an electron. So now you are more negative, right? You have more stress. Your weekends are full. You think about how Mr. O is hanging out over the weekend while you're studying. So you become a more negative person. You become a negative ion. And that's called an anion. Okay. So those are the two different types of ions. Cations are positive, anions are negative. Anions have more electrons than protons, and cations have more protons than electrons. All right, what's up?
Do atoms naturally lose electrons and protons?
Yeah, so in nature, most of them tend to do this. We'll talk about the pattern that we use for this, but I would say usually don't assume ionic charge unless you're told that there's ionic charge, yeah. Okay, so these are the two types of ions. Now, there are some patterns that we can use in order to figure out whether an element will become positive or negative. So I want you guys to take a look at a periodic table in front of you. So if you have your own copy, that's fine. If there's one in a sheet protector in front of you, hey, you can take it out of the sheet protector. That is my gift to you, okay? Such a generous person. So you can either take it out of the sheet protector. Please leave the sheet protectors though. I need those. But if you have a copy of the periodic table, you guys can get one. But just make sure you have one in front of you, okay? Okay, so the pattern for elements and whether they become cations or anions are pretty simple, okay? So let's look at the periodic table. Okay, and if you want to come up here and pick up a copy of the periodic table, I'll put them out right now. Okay, but for the pattern, let's start with the cation. So cations are usually going to be your metals. Okay, so metals usually become cations. Okay, so we talked about the metals last time. It's the guys in the left side and most of the middle. These guys become cations. So just keep in mind that metals, they like to become cations. Okay. There is one little weird exception, and it's hydrogen. Hydrogen is a non-metal, so hydrogen also likes to become a cation. So we'll say hydrogen and the metals, they like to become cations. All right, so hydrogen and the metals like to become cations. And so the ones that want to become anions are your non-metals. So the guys on the right side of the periodic table. So non-metals, they like to become anions. So if you guys notice, most of the periodic table is going to become a cation. They want to become cations because most of them are metals. And we'll go into more details like exactly what charge they're going to have. But there is one group that I do want to mention. It's a group of non-metals, and it's going to be this last column right here. Okay, these are called the noble gases. Okay, and these guys, they like to stay neutral. So the noble gases like to be neutral. All right, so that's the pattern for the elements. Any questions or things you need to clarify? Yeah.
What about the transition?
So transition metals, they all like to become cations still. They're still metals. Good point. There is an exception to a rule we'll talk about later where, so remember what the transition metals are, but yeah, they all like to become cations. Any other questions? Okay, so that's elements. Now, ions are kind of tricky because there are molecules that also like to become ions. Okay, nature is weird like that. So the chart that I passed out to you, those are called polyatomic ions. So you guys can pull that up. It's also on the AP Chemistry Canvas class. If you click on polyatomic ions chart, you can click on that, take you a link, and that's what I just passed out to you. So don't feel like you need to go there right now, okay? And this is for you guys. Another generous gift from me to you. So if you guys take a look at this table, it tells you the molecules that like to become ions. So just like how elements want to become ions, some groups of elements, some molecules also like to be ions. And we got the most common ones right here. Now, you do not need to memorize all of this. I'll be honest with you, I don't know all of them. But the ones that I put a star next to are the ones I highly recommend that you memorize. Like, I'm not going to quiz you on it. Like, I'm never going to be like, what is the chemical formula for acetate? But the ones with the star next to it, and I think the stars are on your paper as well, those are the ones that we use a lot. And so I just recommend that you memorize it either by memorizing it or just by using them in problems frequently. You'll come to memorize it. Okay? But the ones with the stars are the ones that you need to know. Okay? So we'll do, these will make more sense as we do some more practice problems. So just keep in mind, these are molecules that like to become ions. They like to get a positive or negative charge. Okay? Any questions? Yes.
Last year, I know we learned about naming like molecules. How are you going to do that again?
Yeah, that's the entire end of unit 2. Because they're in AP chemistry and they're sad. It's because they're if you notice, they're non-metals. Most of them are just groups of non-metals, so they tend to have a bit more electrons. Yeah, we'll talk about that. I think unit like 7 or 8. Once we start drawing structures, you'll see why they tend to be more negative. Good question. All right, let's move back to the notes. Okay, so there's a pattern that you're going to need to know for the AP Chem test. Please don't copy anything yet. Let me just describe it first, and I'll teach you guys the pattern. Okay, so the pattern is on the periodic table. So depending on where an atom is on the periodic table, depending what group it's in, the columns, it's gonna tend to become a certain charge. So let's go back to the periodic table, and I'll teach you guys what the charge is gonna be, okay? So everybody in the first column, they wanna become +1. That includes hydrogen, okay? And you guys probably wanna write this in your periodic table, okay? Everybody in the second column wants to be +2. Yeah, of course. Yeah. I will pass a stack. Okay, so everybody in the first column wants to be +1. Everybody in the second column wants to be +2. This column right here wants to become +3, but we don't use this that much, so don't stress too much about this. This column also wants to be +3. Okay. This column wants to be -4. This column wants to be -3, -2, -1, and then these guys are neutral. Yeah, what's up? Mm-hmm. What, this one right here?
Yeah.
Or no, they tend to become -4. These guys are kind of special though, carbon and silicon. They actually tend to not form an ion. They don't want to become an ion usually, but if they have to, they become -4. So I would say the ones that you don't really need to focus on are group 3 and group 14. Don't stress too much about these guys because you're rarely gonna encounter these ions. Like teaching AP Chem and going through college Chem, I've seen maybe 1 or 2 problems that required me to know this, like in my entire life. So you don't have to know these ones. But these ones right here, the other ones, those are very important. Yeah. They most likely will not be on the test. So if you remember what's on the screen right now, you should be in good shape. Yeah, I'm just telling you because it's in the book and I want to make sure I'm prepared. I don't want you guys coming up to me later and be like, Mr. Joe, you never taught us this. But it's a safe bet. Right? I know there's a limited amount of memory in here. And so, just use that memory wisely. All right. One thing I do want to mention as well are the transition metals, groups 4 through 12. Okay, these guys have variable ions, okay, which means that they can form multiple ions. So you don't need to memorize these guys. Usually you'll be able to either figure it out or the problem will tell you what the ion is. Okay, so a good example would be iron. Okay, and you guys don't need to write this down, but iron's a weirdo. It likes to be +4, +3, +2. Sometimes it's even +1. Doesn't know what it wants to be. And so you don't need to memorize these middle ones. Another good example would be copper. Copper can be +2 or +1. So there's no like most common ion it likes to become. So you guys just know these are variable. Yes. Zinc and silver, they typically have a most common one, but they can also form other ions. I'll explain how to figure that out towards the end of the unit. But you don't need to memorize. Don't worry about those at all. Yeah, you'll usually get the charge for it, or you can figure it out using the method I'll teach you at the end of the unit. See, these questions are going too far from me. I'm not there yet, guys. Yeah. Oh no, at the end of the unit. I might have misspoke. Yeah, my fault. All right, any other questions? Okay, so one term I'm going to be throwing around a lot is going to be something called most common ion. And most common ions are basically this stuff. What ion does it want to be? Okay, so if I ask you, hey, what's the most common ion for boron? You would just say, hey, boron wants to become B3+, because that's the charge that it wants to be. We'll talk about why they want to be these charges later. Again, that's like unit maybe 5 or 6 or something like that. But for now, just remember this pattern and it should be totally fine for the test. Okay. Any other questions? All right, let's try a couple practice and then and then we'll move on to the next topic. But I want you guys to just take maybe a minute. I want you guys to predict the charge that's expected for the most stable ion of gallium and phosphorus. So find gallium and phosphorus on your periodic table and try to figure out what ion they want to become. Basically, their most common ion. So if we look for gallium and phosphorus on the periodic table, we get Ga and P. So what's the most common ion for gallium? Yeah, 3 plus. So it's just gonna be the way that you would write it is GA, and on top right you write 3 plus. Okay. Yeah. I don't know why they reverse it. Instead of writing +3, they write 3 plus, but that's just a standard notation. I personally will not mark you wrong for doing +3, but on the AP test they might. So I would recommend just getting in the habit of it. Chemists are very elitist about the way they write things. Okay, and then phosphorus, what is the MCI for phosphorus? Yeah, 3 minus. Good. So you guys are getting the habit already, reversing it. Okay. Any questions about that? Alrighty, let's move on. Okay, so now that we talked about ions, let's make them into molecules now. So there are 2 different types of compounds or molecules. And the one that we're going to focus on this time is going to, or for this unit, are called ionic compounds, okay? There are things called covalent compounds, and I'll go over them in just a second. But ionic compounds, it's usually a metal plus a non-metal, okay? So something from the right side of the periodic table and something from the left side. Another way that you can think about it is it's a molecule that has a that's made out of a positive ion and a negative ion. So it's always going to be a cation and an anion, usually a metal or non-metal, but it can sometimes involve some polyatomic ions. So you guys might notice that they're positive polyatomics, negative polyatomics. And as long as they combine with a cation and anion, you get an ionic compound. Okay. And in these situations, the electrons are transferred. Okay. This is in contrast to covalent compounds, or if you guys notice, it's usually a non-metal plus a non-metal, and the electrons are shared. So the difference is that in an ionic compound, the electrons are transferred. In a covalent compounds, the electrons are shared. And we'll come back to covalence later on, but for this unit, we're going to be focusing mostly on ionic compounds, okay? So let me show you very briefly what it means that for the electrons to be transferred. And you guys don't need to copy this down, but here we have an example of an ionic compound being formed. So let's assume that we have sodium. Sodium has 1 movable electron, okay, and chlorine has 7 movable electrons. Okay, please don't ask me why. We'll get into that later on. Just trust me for now. Okay, blindly trust me. Okay, so sodium, what it's gonna do is it's gonna want to give away one of its electrons to chlorine, right? Because remember, the most common ion is +1, right? It wants to lose an electron. So sodium, it wants to give away an electron, and then chlorine, if you guys remember, chlorine wants to become negative, right? So this guy wants to be positive, this guy wants to be negative. So Na is going to be like, hey, do you want my electron? And then it's going to give its electron to chlorine. So sodium is going to give away its electron to chlorine. And once sodium gives away its electron, it becomes positive, right? It becomes happy. But chlorine gained an electron and it becomes negative. So it becomes sad. And then they realize that they need each other because it wants to balance each other out, right? So the positive and negative, they become super close and bam, they get married and they become NaCl. And NaCl is salt. So they become very salty in their relationship. So basically, that's how ionic compounds are formed. Usually the metal gives away the electron to the non-metal, and then they get stuck together because positive and negative attract. Opposites attract. All right. So I'm going to give you guys 2 minutes. I want you to go through the molecules in 12.12, and I want you guys to figure out if they are ionic or covalent, okay? For some of them, you will need to refer back to the polyatomic chart, so just make sure you guys have that handy. But yeah, just try to figure it out, kind of experiment, talk with the people next to you, and then we'll go over the answers, and then we'll move on. It'll take about 3 minutes to do that. Alrighty, can someone raise their hand and tell me what is N2O? Yeah, it's going to be covalent. Okay, so N2O is going to be covalent, and you know that because both nitrogen and oxygen, these are both non-metals. So it's going to be covalent. Okay, good. All right, let's go to Na2O. Could someone raise their hand and tell me? Yes, Susanna. Yeah, this one is ionic, because sodium is going to be a metal and oxygen is going to be a non-metal. So this is ionic. Good. All right, I'll do the next two and then I'll ask for the harder ones from you guys. That way it's easier for me. But CaCl2 is also ionic. Calcium is a metal. Chlorine is a non-metal. And then SF4, these guys are both non-metals. And so this is going to be covalent. Okay. All right, the last two are the ones that were a little bit trickier. Someone raise their hand and give it a shot. Yeah. Yes, this is ionic, okay? And it's because PO4, if you guys notice, is polyatomic, right? So this is a polyatomic ion. This is negative. This is a negative polyatomic ion. Mg is a metal, okay? But it's positive. And so you got an ion, two ions coming together. All right, and the last one, anyone want to take a shot? Yeah, Miles. This is not covalent. It's very tricky. And I know why you said covalent. It's because nitrogen, hydrogen, and chlorine are all non-metals, right? And so the natural inclination, and I probably think this too based on the pattern I told you guys, is, hey, this is non-metal, so it's going to be covalent. However, there's a reason why this is ionic. Anyone want to take a shot at why? Yeah. Exactly. So this is kind of a trick question, so I apologize. Try to trick you guys, but NH4 is ammonium. Yeah, NH4 is one of those weird groups where it comes together and it becomes positive. If you notice, everybody's negative except these couple ones right here, right? And so NH4 is a weird one. And so that's going to be a positive polyatomic. Chlorine is negative. And so this is going to be ionic. But if you put covalent, because they're all nonmetals, your thought process is in the right place. I just try to trick you guys. So I put that one there on purpose. All right, any questions? Yeah, so just be careful. And that's why if you notice there's a star next to NH4, it helps to memorize it because you'll be able to identify it on there, okay? Alrighty, let's try another problem. So now we figured out difference between ionic and covalent. Now we're gonna start putting them together in molecules on our own. Okay, so I'm gonna do one of them with you guys, and then I'm gonna have you guys try some on your own, okay? So let's start with part 8. Let me zoom in a little though. Okay, so now I'm going to be giving you guys ions, and you got to tell me what the molecule that is made is. Okay, so let's do part 8 together. So in part 8, it tells us that we have an Al3 plus ion, and it's going to be combining with Cl minus. Okay, and it's asking you what molecule is going to be made when you add these guys together. Okay, now these guys have their own electrical charges, and so it's positive and negative. They want to complete each other, right? They like to connect. But the thing that you need to know is that the compounds, ionic compounds that are made, so ionic compounds, they want to be neutral. Okay? They want to become neutral. What that means is they want a balance between the positive and negative energy, electrical energy. Okay? I do want to clarify, guys, that I say like they want to be happy, they want to complete each other, but these guys don't have feelings like that. So please make sure when you guys do your FRQs that you don't use language like that, because your grader might read it and think you're crazy, thinking these guys have emotions, okay? Remember, matter is about physical things. Emotions are a type of non-matter, so emotions don't matter in this class, okay? Yeah, that's why I can give such poor grades and hard exams and I'm fine, because emotions are non-matter. I'm just kidding. Your emotions matter very deeply to me, guys. I care very much. All right, anyway, positive and negative electrical energy, and they want to balance each other out. Now, if you guys look at these two ions, if you just put them together, which one do you have more of, positive or negative electrical energy? Yeah, so it's too much positive energy. So it's like a friend group, right? If you got a friend that's way too happy all the time, right? It's not balanced. The friend group's gonna rip apart because you'll be like, oh, I failed my test. And be like, oh, they're so happy all the time. Or like, hey, I'm going to a funeral and be like, oh, let me go with you. Right? It's not gonna work out. You can't be too happy. Right? I had a girl in my organic chemistry lab in college that met at 6 a.m. and she was always happy. And I'm be honest, it frustrated the crap out of me. So I'm like half asleep and she's like talking about how her weekend was. And I'm like, dude, I don't care. Anyway, the point is you want some negative energy to bring that down. So we're going to add some negative chlorines in here to balance out the positive energy. So aluminum is +3. So what we need to do is we need to make it -3 so they can balance out, right? We need 3 sad people in order to bring down this happy person, right? Exactly, just like that. Okay, and so I'm basically Squidward, guys. Anyway, so you put them together, and so you need 1 aluminum and 3 chlorines, and they're gonna form AlCl3. And so this is the ionic compound that's made when you combine aluminum and chlorine ions. Yeah.
That works, but it feels longer.
Yeah, so if that works for you, then do it that way. I'm just doing the long explanation because it's my way of telling a story. And so, yeah, whatever works best for you. If you can just see it and be like, dude, it makes sense another way, then I'm totally cool with you doing it that way. I just wanted to really tell that story. Yeah.
So that compound doesn't have a positive or a negative charge.
No, it does not. It's balanced out. Yeah. All right, you guys think you could try the other ones on your own? All right, let me give you guys 3 minutes. You guys can try B, C, and D together. And then after that, we'll go over the answers and then we shall move on. Okay, so for part B, you should have figured out that you need 2 aluminums and 3 oxygens. Okay, that's how you can get it to +6 and -6. Okay, part C, you had to figure out the charge. So you should have used the most common ion, the predicted charge. Mg becomes 2+. Phosphorus becomes 3-. And so these guys want to become Mg3p2. Okay. And then same thing here, Mg we said wants to become 2+. We got nitrate, which is a polyatomic, and you're gonna need 2 of these. And so the way that you would write the formula is Mg parentheses NO3 2. Okay. So yeah, just make sure you put into parentheses whatever you want to double. Okay, so technically, if you did this N2O6, that's okay. But first of all, you're doing more math in your head than you need to. And secondly, it can confuse whoever's reading it because this might not be nitrate. Okay, you want to make sure you clarify what the nitrate is. So the reason I'm telling you that is because let's take a look back at the polyatomic chart. Okay, take a look at acetate. If you guys notice, acetate is a little bit different from your other molecular formulas because you notice how some of the elements are separated, right? There's 2 C's, there's 3 H's, and there's 2 O's, but they separate it like this. It becomes CH3-Cu, right? Yeah. And the reason why they do that is so that it's easier for the reader to see what the molecule looks like. Towards the end of the year, we'll talk about drawing the bigger structures, but this kind of tells you what the molecule is going to look like. And so just keep in mind that sometimes we write the formula like that in order to show the structure. Same thing with MgMNO3-2. The reason we do that is to show the reader that there are 2 nitrates. A little bit easier to understand the structure. Okay. All right, any questions? Okay, what time do we get out? All right, I'm gonna give you guys a quick 5-minute break and then we're gonna come back and then we will finish up the unit. Okay, so if you need to go to the restroom, go to the restroom. If you want to relax, you can relax. If you want to see the answer key to the test, you can see the answer key to the test. Okay, so on your exam next week, you will have to name, so just a heads up on that. You will not get a form on the AP test or on the test on how to name things, so you're kind of expected to memorize these rules. Now, I'm not going to ask you what's naming rule number 1, obviously, right? I'm going to give you the molecule and you're going to be expected to name it. Or in reverse, I might give you the name and you got to write the formula. And so I'm going to go over the rules that you need to know how to do that. On the AP test, sometimes they'll just give you a formula and be like, hey, figure out like what we're talking about, or give you a name and figure out what chemical you're talking about. So that's why these naming rules are important. Okay, so let's start with the first one. The first one's super easy. Again, we're talking about ionic compounds, so things that are made out of cation and anion. The first rule is that if the metal forms only one type of cation, basically if it means it follows the pattern. So it follows the pattern that we learned about, like with the columns. Then what we do is we write the name of the cation, just write what's on the periodic table. And then we write the anion, but we change the ending to IDE. Okay, so good example right here is KCl. K is potassium. Potassium follows the rule that we talked about, right? It's just +1. So we just write the name potassium. And then the anion is chlorine. So we just change the name at the very end to IDE. So it becomes potassium chloride. Okay. So pretty simple. Just change the ending to IDE. All right. So I will give you guys 1 minute. Try doing CaBr2. I will give you a heads up. It doesn't matter how many anions there are. There could be 50 bromines. You still follow the same naming method. Okay, so the number doesn't change the naming rules. Yeah.
I can't remember if it was like last class or whatever when we were talking about like whatever. Does that have anything to do with this or?
Later.
Okay.
Yeah. Oh, you mean the isotopes?
Yeah.
No, isotopes are completely different from the naming. The isotope naming is just the element name and then the mass number. Yeah. You don't worry about the mass number for ions. Good question, though.
So on the test, you're gonna give us
Yeah, either I'm gonna give you the formula and you gotta write the name, or I'll give you the name and you gotta reverse engineer it into the formula. Yes, and I will give you both. It's my gift to you. A third gift for today. Yeah, I'm like the wise man bringing gifts to Jesus, right? Just like them. But instead of gold, myrrh, and frankincense, I'm gonna give you guys a periodic table, a polyatomic ion chart, and a test. Merry Christmas. Oh shoot, that was recorded. Sorry, parents. I'm just joking. They're not gonna listen to this. Actually, Robert, you said your dad listens to the chem lectures, right?
Yeah.
Oh,
seriously.
Yeah, he watches the lectures on YouTube.
hello, Robert's. Hello, Robert's dad.
We shout
Yeah,
him out.
give him a shout out. Alrighty, guys, let's go over the names. So let's start with the cation. What's the name of the cation? Yeah, calcium Ca is calcium. Okay. Our anion, Br, is bromine, but we got to change the ending to IDE, so it's bromide. Okay. So calcium bromide. All right, pretty simple, right? Okay. The second naming rule is a little bit more complicated. You're just adding one thing on to the first naming rule. Okay, so the first naming rule is for metals that form only one cation. So the things that follow the pattern. Okay, we said earlier with the transition metals, the guys in the middle, the metals in the middle, that these guys right here can have multiple variable charges, right? And so for these guys, you have to write the charge in parentheses, okay? So you just, same thing, you write the name of the metal, you put the charge in parentheses, Roman numerals, and then you want to write the ending, the anion with ID, okay? So this is the one where you kind of have to reverse engineer the formula, okay? Because you don't know the charge on the metal. Okay, so I'll show you guys what that means, and then we'll go over 2 examples, and I'll have you guys try some on your own, okay? So if you guys take a look at the first example, you got iron 2 bromide. Now it tells you that the charge is +2, but how do you know that? Let's say, for example, on the test, I give you this formula and I write the name. How do you figure that out? Now, you don't know what iron is, right? Because iron's in the middle and it could have multiple charges. But you know for sure what bromine is going to be, right? What's the charge that bromine is going to be? Yeah, -1. So it's -1, and there are 2 of them, right? So that means that there are 2 bromines, and they cancel out the iron. So only 1 iron is needed to cancel out the -2. So what's obviously the charge on Fe?
2+.
Yeah, 2+. There you go. And that's the reason why it's iron 2, because of the charge bromide.
When you were
Mhm. Mhm.
Just
Yeah, again, whatever method works best for you, use that method. Yeah. I think I'm a little bit more visual, so I like drawing these, but if you can just do it mathematically, then that's totally fine. Yeah. For these, you'll never have to show your work. So, okay. Same thing with this one right here, iron 3 bromide. The reason why it's 3 is because there are 3 bromines, right? There's only 1 iron that's needed to balance it, so obviously that's going to be 3, and that's where you get the charge. Okay. All right, so I'll give you guys 2 minutes to try 2.15 and 16, and then we'll go over the answers, and then we'll go into some more fun naming rules. Next naming rules. So CuCl2, you should have figured out that chlorine is -1, right? And so there's 2 of them, and so that means chlorine or copper has to have a charge of what? 2. So 2 plus. So the name will be copper 2 and then chloride. Okay. And then for this one, same thing, chlorine is -1, but there's only 1 of them, so the name will be copper 1 chloride. Okay, yeah.
We have to write the one. Is there a copper chloride? And would that be?
No, you have to add the ionic charge. Because copper can have multiple. Yeah. Yes.
how do you
So you only add the Roman numerals if it's a transition metal that can have multiple charges. No, I'm not going to give it to you on the test. No. Any other questions? Alrighty, let's go to the next one. The next one's pretty easy. Okay. So if an ionic compound has a polyatomic ion, I have the chart for you right here. We do the same thing, but instead of changing anything, we just write the name of the polyatomic. We just keep it simple, okay? So for this example right here, we got FeSO4. What we would do is we identify the polyatomic. So what's the polyatomic? SO4, and what's the charge on SO4? Yeah, -2. That would make the charge on iron +2, right? So we just follow the exact same naming conventions we learned. So we write iron 2, but for the polyatomic, we don't need to change the ending to IDE. We just write sulfate. Okay, so super simple. Polyatomics are probably the easiest. You just write the name of the polyatomic. Yeah.
It's not the test.
Yeah. Yeah, for my test, yes. AP test, who knows? Yeah. But I wouldn't go out of my way to memorize them. Yeah, it's not worth it. Usually they'll come with the formulas, and so you can kind of identify them. All right, I'll give you guys like 30 seconds to do 2.17. Should be pretty quick. What is the cation in this molecule? The cation is, I think I heard it. Ammonium, yeah, NH4, saw that earlier, so it's going to be ammonium. Okay, the anion, the -1 is nitrate, so we just write ammonium nitrate. That's it, super simple. Okay, let's move on to the 4th naming rule. The 4th one we're not gonna really go over because like sometimes they use it, but sometimes they don't. But most of the time they don't. So if you guys want to read it for your own knowledge, you can. But if we have a couple of ions in a series, by series we mean if everything stays the same except the oxygen. So if you notice here, the prefix and the suffix might change. So for example, we have ClO3-, which is chlorate. You add an oxygen, it becomes perchlorate. Take away one, it becomes ite. And then if you take away another one, it becomes hypoite. So this isn't that important. You won't see it very often, but it's just something to be aware of. Yes. Yeah, the 4th one, you won't see it very often. On our test, it will definitely not be on it. And the AP test, most likely it will not be on it. Okay. Yeah. Okay. Yeah. Sure. Yes.
And then that's like for like no matter what it is, you always have the per and eight.
Yeah. The complex one is the complex part is that it has to be ions in a series. I'm not going to go over what that means. It just means that if they have the same base, and then you add and take away oxygen, it might change the suffix and the prefix. But yeah. But I'm not like, you're never going to be asked like how many ions are in the nitrogen series. Like nobody's going to ask you that. So just keep that in mind, okay? But I'd say the distinction you want to know is that 8 means there's more oxygens than ite. That's probably the best distinction. And you can tell based on the polyatomic sheet that you have. All right, we're not going to spend too much time on 4. Let's go to 5, and 5 is the last one. For 5, there are molecules that are called hydrates, and hydrates are basically molecules that come surrounded with water. And so that it's part of the formula. So a good example you guys might know of from real life is Epsom salt. I don't know, maybe if you put Epsom salt in a bath or something to reduce inflammation. I don't know, but Epsom salt is magnesium sulfate heptahydrate. And so what that means is magnesium sulfate is connected to 7 water molecules. Okay, so if you want to visualize that, if this is magnesium sulfate, Epsom salt is when there are 7 water molecules that are around that magnesium sulfate. And this whole thing is called a hydrate. It's Epsom salt, okay? So just know what a hydrate is. You might see it and you might have to calculate some things with it. But the way that we do it is we write the ionic compound, we write a dot, and then however many water molecules are around, okay? Yeah, hydrates are only for water molecules. Okay, so you just follow the same naming conventions as before, and then you just put the prefix depending on how many waters there are, and then hydrate. So I'll give you guys about a minute and a half to try 2.18. Try to write the name of this hydrate. And then after that, we'll go into the last practice problems and then we'll be done for today. Just take a minute and a half to do that thing together. Okay, so we have Fe3 parentheses PO4 parentheses 2 dot 4H2O. It's like basically everything we went over. So should have noticed that the anion is phosphate. Okay. Phosphate has a charge of 3 minus. And so if there's 2 of them, it's a charge of -6, right? And so that means that iron has to be iron 2 to balance out the phosphate. So iron 2 phosphate, and then you would have 4, so tetrahydrate. And there you go. That's pretty much it. And on the exam, this is about as hard as it's gonna get. There's not, you can't really make this more wacky than that. Okay. All right, you guys ready for the last problem set? Okay. Let's go on. This was so fun. I love naming. Okay, I will give you guys about maybe 5 minutes to do 2.19, 2.20. If you guys finish early, you can check with the people next to you. I have the answer key for the test if you guys want to check it, if you guys finish early. And then we'll go over them very briefly, and then we'll be all done for the day. Okay. Okay. Alrighty, 2.19a, the formula that you should get is Cu2O. Okay, copper is +1, oxygen is -2. Iron 2 sulfide, you should get FeS. Sodium peroxide, Na2O2. Iron 3 sulfate, you should get Fe2SO4 For FeOH2, you should get iron 2 hydroxide. This one right here, I'm not going to read all that. It's going to be calcium acetate. Okay. Should have noticed that this is a CH3CQ or CH3Cu. This one right here is going to be lithium perchlorate. And then this one is magnesium nitride. All right, and there you go. That's all of them. So that should be the level, or that's going to be like the level of these questions on your exam. So you should be pretty comfortable with those. If you're able to do that without the polyatomic sheet, without the naming rules, then you should be in good shape. I will not give you like perchlorate on the exam. I'm not going to give you peroxide, so don't stress too much. You will have acetate, so keep that in mind. Yeah. You will not be able to use the polyatomic sheet. No. Yeah. Yes. No, just the regular periodic table and the AP equation sheet you had last time. I'm gonna give you the same stuff. Blank, everything blank. Yeah, so that's a good question, guys. So just a heads up for the exam, you're gonna get a blank periodic table. So that means you're gonna have to know the pattern. You're gonna need to know where the metals and non-metals are. I'll actually tell you what the FRQs are gonna be on, just so that you guys have a little bit of a little direction in your studying. For studying, again, just do practice problems. Reading the text is good, but you don't need to study the content so much. The most important thing is doing as many problems as possible. If you do the problems in the back of the book and you want to check your answer, that's not homework. More than happy to send you a copy of the answer, so just let me know, okay? But for your test, your MCQ is going to have 7 questions. Again, you're going to need to know isotopes. You're going to need to know polyatomics. Then you need a name. Yeah, that's pretty much most of your MCQ. FRQ, you're gonna need to know how to read and draw a mass spectra, so keep that in mind. And naming. So those are 2 FRQ questions. So I'd say relative to the previous one, it's a lot easier if you're comfortable with that. But don't get complacent because there are some questions that might make you go like, yeah, just keep that in mind.